And okay, please, those of you at home, let me know if you can see the screen with the notes on it. And do I have my video going? And if you can hear me. Let's see. Yes, we can, both. Hoorah. Okay. Why don't you guys turn on your microphones and say good morning to everybody sitting here in the classroom. No? No action? There it comes. There it comes. Back in business. Don't forget to get the format. Make sure you get that in the format. That one. Okay, camera. Good morning. Happy Tuesday. I want to continue what we were doing last time, but I'll certainly be glad to start the class answering your questions. Okay, I'm a little bit behind on web work. If you want to get some posted, I got some up there for you now.
Are you working optimization problem?
I'd love to. Can you tell me what and where?
It's question 10.
Can you kind of read it to me, or do you need to call it up?
Consider a window, the shape of which is a rectangle of height h, is surmounted by a triangle having a height t that is 1.5 times the width w of the rectangle. The cross-sectional area is a, determine the dimensions of the window which minimize it.
Okay, determine the dimensions of the window that do what?
Minimize the perimeter.
Now, there was a piece of information about t that I couldn't quite remember. T was 1.5 times the width?
Yes.
T is the height of the triangle?
Yes.
Is it an equilateral triangle or just any triangle?
It just says triangle.
1.5 times the width. Okay, so area is the number A. We'll just use that as a constant. If you want to put a real live number there, you can, but we'll just use the letter A. We've got a window that is this rectangle with dimensions W and H, surmounted by a triangle of altitude T. We know the area of the window is the number A, and T is 1.5 of W, and our objective is to minimize the perimeter. So in the perimeter, we need to go around. Let me mark the perimeter in red. We have everything labeled here except we got a W here, we got an H there. We're going to have to stick some sort of variable here and here. I'm assuming that that's an isosceles triangle at the very least. And then that is H. And so for now, let's just stick the variable X over here. That the sides of the triangle are X. And we'll write that in terms of W, I suppose. So now let's write our parameter in terms of X, H, and W. That our perimeter is 1w plus 2h plus 2x. And what we would like to do is get that objective function in terms of only one variable. So one thing we can do is we can, let's see. Well, I can't do anything with t and w yet because I don't have a t in here. Let's go back up in here. This is w, so this over here is 1/2 w. We can look up here at this right triangle and write the Pythagorean's theorem for that one. That right triangle says that 1/2 w squared plus t squared is equal to x squared. So if I wanted to, I can get maybe the x out of here. That x is going to be the square root of all of that. So that says x is the square root of w squared over 4 plus t squared. Now we know that t is 1.5 of w. Let's take that and put it in where the t is here. And so now we have that x is equal to the square root of w squared over 4. Let's write that as 3/2 w. And so when we square that, that becomes 9/4 w squared under the square root sign. And we can put those two together. I have 9/4 w squared plus 1/4 w squared to give me 10/4 w squared. And so now let's simplify x to be the square root of 10 times w over 2. So there's our x. We're going to get that out right here. That'll give our parameter in terms of w and h. We want our parameter just in terms of w, so let's use the overall area formula. So this particular problem, we had to write two side equations. Our first side equation was here. And now our second side equation will involve the area. We've got the area of the rectangle plus the area of the triangle is going to equal to the number a. So the area of the rectangle is w times h. The area of the triangle is 1/2 its base, which is going to be w, times its height, which is t. That area should be the number a. Now, t is 3/2 of w, so let's replace that here. And I have that wh plus 1/2 w times 3/2 w is equal to a. Let's see, 3/2 w plus 1 w will give me 4/2 or 2 w. So I have wh plus 2 w is equal to a. And I'm going to take this equation and solve it for the h. I'm going to move the 2w over, and I'll have wh is equal to a minus 2w, and now divide by w. And so we have h is, let me simplify it as a over w minus 2. That's going to go right here. That's going to allow me to write my perimeter function strictly in terms of the variable w. Yes? How did I get 2w? I want area. Okay, so let's see. Right? Oh, you're right. That's 3/4 w squared. Yes, I lost a square. So 3/4 is 2. That's a w squared. Okay, so that's a w squared, which gives me a w right here. Thank you. Thank you. Good eye on that one. Wait a minute. 3/4. Oh, right. 3/4. I'm multiplying. Good freaking night. Let's fix everything. That's 3/4 w squared. And so that's a 3/4 w squared. And so that is a 3/4 w. Numbers. Now, is that better? Okay, so let's rewrite our perimeter function now. Good. So we have our objective function is P is equal to W plus 2 times H. So A over W minus 3/4, and that is a W, plus 2 times X, and X we got up here as square root of 10 over 2 times W. That's the function that we're eventually going to take the derivative of. Let's simplify it by quite a bit. So send the 2 through the parentheses in each case, and I have P is equal to W plus 2A over W. One of the 2's cancels here and gives me 3/2 W. 2 cancels here to give me square root of 10 times W. I can put this one together with that one. That's 2 over 2 minus 3 over 2 W. And I have perimeter is equal to, let's see, minus 1 over 2 W. And then let's write that plus square root of 10 W plus 2A over W. I think that's okay. We're looking for where that is a minimum. So we're looking for a critical number. Let's go ahead and take a derivative. Treat A as a constant and treat this over W as W to the negative 1 power. Here comes the derivative for you. P prime is negative 1/2 plus the square root of 10. Now this is going to be minus 2A W to the negative 2, which I'm going to put down here as a W squared. Now we're going to replace P prime with 0. And we're going to solve this for W. Okay, so let's move the numbers to the other side. Well, heck, let's move the 2A over W to the other side. Yes. W squared, 2A over W squared. Let me write that as the square root of 10 minus 1/2. I'm going to multiply through by w squared. Then I'm going to divide by the square root of 10 minus a half. And then we'll take the square root. If you quickly did the second derivative test to check if that's a minimum, the second derivative, this is a constant, so that derivative is 0. This is minus 2a times w to the negative 2, so I get a positive 4a over w cubed. This is a positive number. When I put it in there, I get a positive second derivative. Second derivative is positive, gives us the smiley face, which reminds us that our critical number down here is a min. And I suppose you have to get all of the dimensions, right?
Yes.
And
Well,
so
that's for the dimensions of the triangle.
the dimensions of the triangle?
Yes.
Okay. So the dimensions of the triangle, how does it ask it? Does it want? You just
Oh,
need.
no. The dimensions of the window. So it asks for H and W.
So H and W. We got us a W. Let's go find us an H. Let's see, back on the previous page, we have H. H, where's my H? Right here. You get H, we take A divided by W minus 3/4 of W. So we got to plug that funky number in for each W. That's where cutting and pasting comes in handy. Lovely number, lovely. So the dimensions that give the minimum perimeter have H and W to be the two funkiest numbers that you will see all day. Especially since one of your numbers has a letter in it. That was a deeply involved problem. That had a lot to it. I didn't realize that when I first read it halfway through. I put more reasonable ones on there, but what the heck? Did anybody follow any of that? Got another one? Anybody at home have a web work problem? Let me figure out where we were as we ended class, because I ended class in the middle of a problem. Yep. But I don't have the problem that I ended in the middle of. Bummer. Any of y'all have the problem that we ended in the middle of? We were breaking a particular area under a parabola up from -1 to something. I don't remember the exact problem. I wanted to start it all over again.
it f of x equals x squared plus 1?
We'll take that. Thank you. First thing we did is we made rectangles to approximate the area between f of x is x squared plus 1 and the x-axis from x is equal to -1 to x is equal to 3, I believe. And we did this first using a left sum, then a right sum, and we did this with 4 rectangles, and then we repeated it with 8 rectangles. So this time let's do it using n is equal to 6 rectangles. Okay, so let me draw you the picture. There's the y-axis here. Let's see, when x is -1, y is equal to 2. When x is 3, y is equal to 10. Didn't leave my scale big enough. Bump that down a little bit. All right. There we go. That's -1. That's 3. That's up here at 10. And when x is 0, y is 1. So it's this piece of the parabola right there, boxed off here and here. When we're using 6 rectangles, we want to make 6 rectangles that are the same width. So we determine the width by taking the right endpoint minus the left endpoint and dividing it by the number of rectangles. So first, the width of each rectangle is given by delta x, which is b minus a over n. So in our example, our delta x is 3 minus a -1 over 6. That's 4/6 or 2/3. So when I put 6 rectangles in here, they all have to be 2/3 of a unit wide. And so if I start with -1 and add 2/3, this edge here would be at -1/3. Then let's add 2/3 to -1/3, and that puts us at +1/3. Make another rectangle. Then 1/3 plus 2/3 gives me 3/3 or 1. Plus 2/3 gives me 5/3. Five-thirds plus 2/3 puts me at 7/3. And then 7/3 plus 2/3 gives me 9/3 or 3. So there are my 6 rectangles. 1, 2, 3, 4, 5, 6. And hopefully they look about the same width. Or close enough for me. It's even bigger. Okay. Okay, so those are the subdivisions. when we make a left sum, we draw rectangles connecting the left endpoint for each rectangle. So if you want to number your rectangles, there's 1, 2, 3, 4, 5, 6. So I'm going to draw the left sum. This rectangle comes over here like that, gives you a little bit too much area. This rectangle is underneath, so it gives you less area. That one's under, under, and under. The height of the rectangle would be the value of the function at each of the left endpoints. So, using a left sum, we're going to make the sum of the values of the function at the leftmost x, and then we're going to multiply it by delta x. And so we're going to have, my function is x squared plus 1. So our first is going to be negative 1 squared plus 1. I'm going to factor out the delta x at the very end. Then I'm going to have a negative 1/3 squared plus 1. Then I'm going to have a positive 1/3 squared plus 1. Now I'm over here at 1. So plus 1 squared plus 1. Next is the 5/3 squared plus 1. And then finally 7/3 squared plus 1. All of that times my delta x of 2/3. So there's rectangle 1, 2, 3, 4, 5, 6 rectangles right there. Those are their heights. Height times width gives us the overall area. Are you with me to there? Yes. Here, it's in the formula.
Oh, yeah.
Left endpoint squared plus 1. So if you don't mind, I won't crunch those numbers. Let's leave the numbers as they said. If you want to do them, you can, and you can tell me what you get. Next, I want to calculate a right sum. So when I make the right sum, I'm going to draw that with my red pen. In my first rectangle, I make my height using the endpoint at negative 1/3. And then my endpoint for the second rectangle would be at positive 1/3, then at 1, then at 5/3, then at 7/3, and then finally at 3. So I use these guys as the x's that I'm going to plug into my function, and that the delta x is still the same. And so our right sum is going to be the sum of the value of f at each right endpoint that I have put the red dot underneath times the delta x. So it's going to be all of these guys, and then the last one's going to have plus 3 squared plus 1. But let's write it out. Negative 1/3 squared plus 1 plus a positive 1/3 squared plus 1 plus the 1 squared plus 1 plus the 5/3 squared plus 1 plus 7/3 squared plus 1, and then finally plus 3 squared plus 1. All of that times the delta x of 2/3. So again, here's rectangle number 1, rectangle 2, 3, 4, 5, 6. And that's height times width, all the way down the line. The more rectangles we put under here, the closer we will get to the actual area. And so instead of crunching numbers, we'll put more rectangles in here using symbolic manipulation. in the symbolic manipulation, we're going to get to a step where we're going to need some formulas. So I'm going to give you the formulas right now, and then we'll go do this in general for n rectangles. So the big idea is that more rectangles will better approximate the actual area. But instead of crunching out more rectangles, we're going to use calculus. We're going to let the number of rectangles get infinitely large. And as we do that, the bases of each of these rectangles will get really tiny, so that we are coloring in the area under the curve with straight line pencil marks, butted up against one another. Okay, so we're going to do this symbolically. We will do this symbolically. And for the sake of argument, we'll use a right sum. Not that it matters. Because again, we're going to have an infinite number of rectangles. Eventually, the right end point is going to fall right onto the left end point. So we will need some summation formulas. The first one is that if you add up a bunch of ones, I'm going to use k as my counter. So if k is equal to 1 to n, and I add up n ones, so that means 1 plus 1 plus 1, keep going until I have n of these. Well, if I add up 3 ones, my total sum is 3. If I add up 5 ones, my total sum is 5. And so if I add up n ones, my total sum is going to be n. The next formula I want to use is that if I add up the first n integers, 1 plus 2 plus 3 plus 4, until I'm out here at n, typically when we add things from left to right. With this formula, it's kind of easy to explain if we don't add things from left to right. If we add things from here, if we add the first one with the last one, I get n plus 1. The term right before this is n minus 1. If I add that with 2, n minus 1 plus 2 gives me another n plus 1. The one before this is n minus 2. N minus 2 plus 3 gives me another n plus 1. So if I add outside to first to second, outside to third, like that, I'll always get a bunch of sums of n plus 1. And the number of sums I'll get would be the number of pairs that I can form here. If I have n things that I'm adding, the number of pairs is just half of n. And so I'm going to get a sum of n plus 1, a total of n divided by 2 times. Try it out. Add the first 10 numbers together. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Look at how I'm doing it. I'm doing 10 plus 1 is 11. plus another 11, plus another 11, plus another 11, plus another 11. So I'm making 5 sums of 11. So this should be 5 times 11, or 55. But now let's add it by brute force. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 15, 21, 28. 28 plus 8 is 36, plus 9 is 45, plus 10 is 55. Shebang. Up here, try this formula. 10 times 11 is 110, divided by 2 is 55. So by gosh, it works. The next formula that we're going to need is the sum of the first squares, n squared integers. So that's adding 1 squared plus 2 squared plus 3 squared on out to adding n squared. And so I'm going to give this one to you. That one is n times n plus 1 times 2n plus 1 divided by 6. Let's verify this formula for n is 3. For n is 3, we have 1 squared plus 2 squared plus 3 squared. So we have 1 plus 4 plus 9 is 14. Now up here in this expression, when n is 3, I have 3 times 3 plus 1 times 2 times 3 plus 1 over 6. So that's 3 times 4, 6, 7 times 7 over 6. Let's see, 3 is going to go into 6 twice. 2 goes into 4 twice. 2 times 7 is 14. For this example, I don't think we need any more, but there is one more formula, and it's the sum of the first cubes. That one looks like n squared times n plus 1 squared, right? N squared times n plus 1 squared over 4. I won't make you memorize these, but I do need to use them in order to do my calculations in the example when we do this in general. All right, so here comes the Riemann sum, the product of some heights with widths. So let me scoot this over, and I'm going to pull it back up here in a second. So back to our example. In our example, our delta x, which in general is b minus a over n, is going to be 3 minus a negative 1 over n. So delta x is 4 divided by n. We're going to generate all of the right-hand endpoints. So we're starting at x is negative 1. To get to the first right-hand endpoint, I take negative 1 plus 4 over n. The second right-hand endpoint, I add another 4 over n to that. And then I add another 4 over n and another 4 over n. So let me draw the number line here, and you can pretend the curve is above it. So here's negative 1. Here is 3. The first right endpoint is going to be negative 1 plus 4 over n. I'm adding a delta x to it. And remember, that's how I got these numbers back over here. I started with negative 1, and I added 2/3 to it. Then I added 2/3, 2/3, 2/3 more. I'm just doing this in general, starting with negative 1, and I'm adding a delta x to it. So now if I add another 4 over n here, I get to the next endpoint. So that's -1 plus 2 times 4 over n. So there's my first right endpoint, there's my second right endpoint. My third right endpoint, I add another 4 over n here. And so this will be -1 plus 3 times 4 over n. So that if I continue this progression, the kth, should I use a k? Yeah, the kth right endpoint is going to be -1 plus k multiples of 4 over n. And so when I write my sum, I'm going to have my summation of f at each of these right endpoints times my delta x. Now let's use our general formula for our right endpoint. And our function, recall, is x squared plus 1. So I'm going to form the sum from k is equal to 1 to n. F of this, let me write that as 4k over n, times my delta x. But delta x is 4 over n. And f is this guy. And so it looks like the sum from k is equal to 1 to n, x squared, so here's the x, squared plus 1. And then I have to multiply that by delta x, but delta x is 4 divided by n. Now we're going to try to simplify this by multiplying out the squared term and combining like terms. Then we'll distribute the 4 over n. So this is the particular function times the delta x. Now we're going to simplify it. So it's a big old algebra problem now. -1 squared is going to give me a 1. The middle term is going to be 2 of these products. So 2 versions of minus 4k over n is going to give us minus 8k over n. Plus the last term squared gives me a 16k squared over n squared. Plus this one times the 4 over n. So let's take this one and that one and make them 2. Then I'm going to multiply 2 times 4 over n and get 8 over n. Then I'm going to multiply these two together, which gives me a negative 32k over n squared. And now I'm going to multiply these two together, and I get a positive 64k squared over n cubed. So that's within the summation symbol. So right now, this is a finite sum. I can add them term by term. I can add all of these, then I can add all of those, and then I can add all of those and put them together. So that's what I'm going to write next. I can distribute the summation symbol in a finite sum. Now these are summations on the variable k. So I'm going to leave the k within the summation symbol, and I'm going to pull the coefficients out front. Over here, when I pull out the 8 over n, it leaves behind a factor of 1. Now I'm going to pull out the 32 over n squared, and it leaves me a k behind within the summation symbol. And then I'm going to pull out the 64 over n cubed, and that leaves me a k squared in here. Here's where our handy dandy formulas come into play. I have a formula for each of these. In closed form, without the summations. We know what those sum to. From our formula page, I'm going to use the sum of sum of ones added together n times is just n. The sum of the first k counting numbers is n times n plus 1 over 2. And the sum of the first squared numbers is this n times n plus 1 times 2n plus 1 over 6. I'm going to put those where I have the boxed expressions. And so we have 8 divided by n times n minus 32 over n squared times n plus 1 over 2 plus 64 over n cubed times n plus 1, 2n plus 1, all over 6. No more dependence on the variable k. And now remember what our goal was. Our goal was to take this expression and let n go to infinity. When we let the number of rectangles become infinitely large, this gives us the exact area. And so our exact area is equal to the limit as n goes to infinity of this expression here. So I'm going to put that here, but I'm going to cancel this pair of n's right here and get 8. Then I'm going to have minus, let me go ahead and cancel the 2 with the 32 and get 16. n plus 1 all over n squared. In here, I can cancel, let's see, 64 and 6 are both even. So let's put a 3 here and a 32 here. And let's even cancel one of the n's here. So I have plus 32 n plus 1, 2n plus 1 divided by 3n squared. Are you with me? All right, the rest is calculus. Here comes the magic. We take these limits. This has nothing to do with n, so as n goes to infinity, this stays at 8. Here, as n goes to infinity, look at what happens if you multiply out the numerator. You'll have an n squared plus 1. So your highest power would look like an 8n squared plus lower powers. Here, if you multiply this out, you're going to have a 2n squared times 32 divided by 3n squared. Do you remember how to take the limit when the degree on top is the same as the degree on the bottom? It's just the ratio of the coefficients. So we're going to pick out the ratio of the coefficients of the highest power of n. So these limits to infinity give us the ratio of the coefficients of the highest power of n. Because I know the degree on top is the same as the degree on bottom. And so we're going to get 8. This is going to be an n squared times 16 divided by 1n squared. So that's just going to give me the 16. This is going to be 32 times 2 times n squared, which is 64n squared over 3n squared, plus lower terms. So I'm going to get plus 64 over 3. So 8 minus 16 is a negative 8. Let's get a common denominator of 3. So that's going to be 24 thirds. 64 thirds minus 24 thirds is 40 thirds. To be the exact area, if I did my numbers right. Is that cool or what? Let's do another one that's more believable. Let's do one that we could figure out the area using geometry. Then let's use these infinite sums, and then we'll see if we get the same number. Okay, so let me first write down the definition of what I just did. 1, 2, 3, this is page 4. Go all the way back to this very beginning right here. And I'm going to write that out in general. So I'm going to use my left endpoint as A. This is K times delta X, and that's delta X. So in general, the exact area under a curve, so given a positive curve, y is equal to f of x above the x-axis from x is equal to a to x is equal to b, we compute the exact area as follows. We first get the width of each rectangle, is equal to delta x. Let's not use an equal to, let's use a colon. And that's b minus a divided by n. Then we get the height of each rectangle. If we're using a right sum, we start with the right endpoint. We add k multiples of delta x, and then we evaluate f at that, where the delta x is b minus a over n. And then we form this infinite sum. We take the sum from k is equal to 1 to n of f of a plus k times delta x, multiply that by delta x. Then we take the limit as n goes to infinity, which forces the delta x's to 0. That special kind of sum gives us the exact area and this sum, this is called a Riemann sum. So when we're doing a right sum, we're making a Riemann sum. When we're doing a left sum, we're doing a Riemann sum. We're going to take the limit as n goes to infinity to get us that exact area. Okay, so let me think of an easy one. Let's take the line y is equal to 4 minus 2x, and let's find the area under that curve from x is 0 to x is 2. Find the area beneath f of x is equal to 4 minus 2x above the x-axis from x is 0 to x is 2. I chose this one because we're going to do it with geometry. Then we'll do it with a Riemann sum. And then I'm going to show you the connection between this and the antiderivative of this function. So draw that graph. It's a line with a negative slope, y-intercept of 4, and look there, the x-intercept is 2. So it's the line right here. The area that we're looking for is the area of that triangle. Quick, what is the area of that triangle? You have a definition of quick? 1/2 base times height, 1/2 of 4 times 2. Right? Area is 4. So by geometry, the area is 1/2 of base times height times base, but either way we're going to get 4 square units. Okay, now let's use the Riemann sum. Okay, so now let's use the Riemann sum. So our first step, I said, was calculate delta x. B minus A divided by N. My A is 0, and my B is equal to 2. So delta x is B minus A divided by N, 2 minus 0 over N. Delta x is 2 divided by N. Next, we find the height of each rectangle that we're going to put in here. The height is going to be F evaluated at A plus K times delta x. F is 4 minus 2x. This is my x. So there's my height. My delta x was 2 over n. So I can write this as 4 minus 2a plus 2k over n. There's my height. Okay, right endpoint plus k multiples of the adder, my jump. My formula is 4 minus 2x. There's my x. But I'm going to let delta x be the 2k over n, or the 2 over n that I computed. Now we put those together. The sum of the f of a plus k delta x times the delta x. The sum from k is equal to 1 to n of, let me write down the general formula. Now let's write it down for this particular function. There's my f. Times my delta x. We need to simplify that as much as we can, and then we'll apply that limit on our summation symbols. So I'm going to distribute the 2 over n through here, and at the same time distribute the minus 2 through here. So that I'm going to have 3 terms in my summation symbol. So 2 over n times 4 gives me 8 divided by n. This is a minus 2a times 2 over n gives me a minus 4. Oops, we know what our a is. Our a is 0. Oh, good. Our a is 0. So let me get rid of that. Our a is 0. So that term is gone. So I'm going to have a minus 4k over n times 2 gives me a minus 8k over n squared. Are you with me to there? Then we're going to do what we did before. Our summation is on the variable k. I'm going to write this with 2 summation symbols. And I'm going to factor out the non-k terms. And so that gives me an 8 over n times the sum. K is equal to 1 to n, and I'm going to replace that with a 1. I factored that out. Here I'm going to factor out the minus 8 over n squared. And it leaves me the sum from k is equal to 1 to n of the k. So now we're going to take the limit as n goes to infinity. To get the exact area is the limit as n goes to infinity of what's left. 8 divided by n times this sum minus 8 divided by n squared times that sum. But again, we can get these strictly in terms of n using the formulas that I gave you early on. The sum of 1 added together n times is just n. The sum of the first n counting numbers is n times n plus 1 divided by 2. So now use our summation formulas. That the area is equal to the limit as n goes to infinity. So this formula gives me n. And this one gives me n times n plus 1 over 2. We can simplify those. Those cancel. And I get an 8. 2 goes into 8 4 times. One of these n's cancel. And I have that. So that's an easy limit to take. The 8 is all by its lonesome. So its limit as n goes to infinity is still 8. When you multiply this out, you get the polynomial that is degree 1 divided by a degree 1. So as n goes to infinity, I just get the ratio of the coefficients, the 4 over 1. And so we get 8 minus 4. And there is the same area that we got a minute ago. Wasn't that fun? But that was a lot of work to get the actual area when we could do this with geometry. And just like in the beginning of this course, we put a lot of work in finding the derivative by using that difference quotient. But nobody in their right mind calculates every single derivative using the difference quotient. Nobody in their right mind calculates area using a Riemann sum every single time. There is a connection between a Riemann sum and an antiderivative. Okay, so let's make the connection. Between this Riemann sum and our concept of integration. Okay, we're just going to do it by exploring. I want you to find the antiderivative of the function we started with, which was 4 minus 2x. Remember, we can do this term by term. What did we take the derivative of to get a 4? 4x. What did we take the derivative of to get 2x? Just an x squared. Let's call this capital F. Remember, our antiderivatives are capital F. Our two endpoints of this particular interval where a is 0 and b is 2. So I want you to find f of 2 minus f of 0 for this particular antiderivative. F of 2 is going to be 4 times 2 minus 2 squared. F of 0 is 4 times 0 minus 0 squared. And I get 8 minus 4 minus 0. 8 minus 4 minus 0 is 4. That's our area. It's the value of the antiderivative, and take the difference of the antiderivative over the range on the x-axis. Let's go back to the first example we did. In our first example, we computed the area beneath f of x is x squared plus 1 from x is -1 to x is equal to 3. Let me dig back to our answer. And we got (40 divided by 3) square units. So let's try it using the antiderivative. Let's compute the antiderivative of x squared plus 1. You integrate x squared with the power rule. You add 1 to the power and divide by that new power. And so you get x cubed divided by 3. The antiderivative of the 1 gives us x. Now remember, we got constants of integration. We don't really need them because we're going to take our antiderivative at each endpoint and subtract. So if there's a constant added here, and when I subtract it, it'll subtract itself out. That's our capital F. Our next step is to find f at the terminal endpoint minus f at the initial endpoint. F at 3 minus f at 1. So let's put a 3 in here. We get 3 cubed divided by 3 plus 3. And now put a 1 in there. 1 cubed divided by 3 plus 1. Where? Oh, a negative 1? Yes, negative 1. Thank you. All right, 3 cubed is 27. 27 divided by 3 is 9. 9 plus 3 is 12. Negative 1 cubed is a negative 1. So I have a negative 1/3 plus a negative 1 is a negative 4/3. So I need to add 12 with 4/3. 12 is the same as 36/3. And so I get 40 over 3 yet again. So I vote that when we want to find area, we will use an antiderivative. But I do want you to know how to do one or two of these by the definition, by the Riemann sum. So I put one or two on your web work. So the big result of the day is that we have this thing called a definite integral. Let me see how many. A definite, D-E-F-I-N, uh-oh, can't spell definite. A-T-E, E-T-E, I-T-E, good. We put our integral of our function here with respect to x, and then we put our a and our b here. Those are the numbers on the number line from left endpoint to right endpoint. This s represents a sum. It does the same thing that our little Greek letter sigma did, but now it represents an infinite sum of heights times width. The dx comes from the delta x. So height times width. And we're summing these from x is a to x is b. But what we saw on the last page was that you first find an antiderivative, and then you evaluate the antiderivative over that interval. Well, we know that the derivative of capital F gives us little f. And we do that as f at b minus f at a, and that's equal to the area under the curve of a positive function f above the x-axis from x is a to x is b. That's our definition of the definite integral, but it's also something that reunites the derivative with a sum. And it's going to be called the first fundamental theorem of calculus. My gosh, if it's fundamental, you ought to know it. It says to compute a definite integral, you find an antiderivative, and then you find the difference in the values of the antiderivative at each endpoint. If f is a positive curve, the number that you get can be interpreted as area under the curve. If f is an arbitrary function, it's just the sum of all of the values of the antiderivative over that interval. So it doesn't strictly represent area, but it can represent a sum of all of these values from A to B. So, for instance, this has a geometric interpretation. We don't know how to compute this antiderivative because of the square root sign. I can't just go in the square root sign and get a 4x minus x cubed over 3 and then put the square root sign back on. Can't do that. And I can't take the square root of each term. So what I want you to do is think about the geometry of this. I'm describing here with an integral sign an area under a curve. What does the graph of y is equal to the square root of 4 minus x squared look like? Maybe you'll recognize it if I square both sides and then move the x squared over. That you recognize, right? Y is equal to x squared plus y squared is 4. That's a circle centered at the origin of radius 2. When I take the positive square root, then I'm only looking at the top half of the circle centered at the origin of radius 2. The area of a circle of radius 2 is pi times 2 squared. So 4 pi is the whole area. And since I only have the top half of the circle, I have to cut that in half. So the value of this integral is going to be 2 pi. Top half of the circle. So I didn't do any calculus because we don't know how, but that's what it does. I'm going to add some details about properties of the definite integral, let you get some practice computing the definite integral, but that'll have to wait until Thursday because, by gosh, I think we're out of time. That was a lot. Trying. Any questions at home? I'm going to cut you off then. I'm going to knock off the Zoom meeting. Can't wait to get you guys back in class. Because when we're in class, we're sitting here eating donuts and drinking soft drinks. I made the donuts myself. All right. Oops, in case you're still writing.
Have a nice day.
Thank you. That's all right with me.